Hey everybody, today we are going to learn about linear functions. Now, we've already been learning about functions, right? We started with relations, a relationship between two variables, and then a function just got a little bit more specific, right? There were extra rules with a function. What was the extra rule? You're not allowed to repeat a domain value or an x value, right? Meaning you can't have 2 comma 1 and 2 comma 5, right? That would be a relation, but that's not a function. But specifically what we want to talk about today are linear functions. Now, linear functions are interesting because that's almost what all of algebra leads up to, right? So the main idea with linear functions is the fact that you plug in x to get y. That's what we're doing. You plug in x to get y. So basically what I want you to think about from now on, whenever you hear a function or you think about a function, it's just something that you plug numbers into, right? You plug in x to get y. That's the input versus output, right? You put something in and you get something out. Now, the most famous, I guess I would say, equation, or the most famous form of an equation that I know you're all familiar with, is y equals mx plus b, right? Slope-intercept form. Every algebra student is familiar with this formula. Y equals mx plus b, right? Now, usually we say m is the slope, b is the y-intercept. We're not even going to get into that with this lesson. Right now, we're really just trying to get the basics of these things and get the idea of plugging in x to get y. So, if this is what the equation looks like, that means we could have something like this. Y equals, let's say, 2x minus 3. Just a good old regular equation in slope-intercept form. This is a linear function because I can plug in an x value to get a y value. So what I'll do is I'll just make up some x values. How about we plug in 0, 1, and 2? And let's just see where that takes us. So if I plug in 0, that would be 2 times 0 minus 3. Now, 2 times 0 is 0, so 0 minus 3 is going to give us negative 3. So I'll put a negative 3 right here where 0 is. Next, I just go through and I plug in 1 and I plug in 2. So, what do I get when I plug in 1? Well, 2 times 1 is 2 minus 3, and 2 minus 3 is negative 1. So when I plug in positive 1 for x, I get negative 1 for y. And we'll do the same thing with the number 2. So if I plug in 2 here, we'll get 2 times 2, which is 4 minus 3. And then 4 minus 3 is positive 1. So when I plug in positive 2 for x, I get positive 1 for y. So this is my table, right? So we started with the equation, y equals 2x minus 3. And the result was this table. Now, obviously, I could plug any x value in. I chose numbers that I could fit on my graph. So a linear function can be represented with equations and tables, and a table can be used to make the graph. So if I take x, right, this is the x-axis, this is the y-axis. X is 0, y is -3, so 0 and then -3 gives us a point right down here. 1, -1. So when x is +1, y is -1. We'll get a point right here. When x is +2, y is +1. So here's +2 for x, +1 for y. Now you might notice these 3 points here, they all kind of form a straight line. Oh, you mean like the fact that the word linear has the root word line? Yes. So a linear function is going to have a line as the shape of its graph. So what I can do is just literally draw a line through them. This is one way that you can always graph a line, right? If you're ever tasked with graphing a line, if you're given the equation, just make a table. Pick 2 or 3 points or 2 or 3 x values to plug them in and get your y values, right? You know, there are other ways to graph, but this is probably the most basic one because you're just plugging in numbers and doing some simple math to get the graph out of it. So right now, what I'm trying to get you to do is build an understanding that all 3 of these are the same, right? Get rid of the work down here. Right? So this equation, this table, and this graph are 3 different ways of showing the exact same thing. Sometimes the equation is necessary because it helps you see things, and we'll look at that in a little bit. The table sometimes is nicer if you want to see a lot of the values actually listed out. And the graph is more of a visual representation, right? There are ways to interpret the graph as well. Again, things that we will be doing later on. So equations, tables, and graphs. These are the 3 main components of linear functions, the basics, right? So let's look a little bit more at the equation itself. Because the real point of this is for you to be able to interpret a linear function, right? You know, if you're going to be taking the keystones, a lot of the keystones are going to ask you to analyze things, to interpret things, right? So when you look at y equals mx plus b, again, a lot of people call this slope because it is, and this y-intercept, again, because it is. But slope and y-intercept, that doesn't really help you interpret the meaning of things, right? Because what this m really means is the rate of change, right? The rate of change. So how something changes over time, right? And the b is your starting point or extra value. So first, let's go back to rate of change, right? A lot of times, this could be a cost per item, right? A lot of times it's like $5 per gallon or, 3 cents per pound or something like that. $5 per mile. The key thing there, the word per, right? So it could be the cost per item. Really, there's some simple words. Let's simplify it even more, right? Usually it is a cost, right? But it could be other things as well. So this could be an increase or a decrease, right? So if something is going up, right? Maybe you're climbing a mountain and you're going 500 feet per minute. Or maybe you're flying a plane and you're descending at an altitude of, 1,500 feet per minute, something like that. I don't know plane speeds. But you're looking for increases or decreases, right? And there are some key words to help you identify the rate of change. Words like per, each, and every, right? $5 per gallon, that's a rate of change. $3 for each banana, right? $3 for each, that's a rate of change. Again, $5 for every hour. You get $5 for every hour. So 5 for the first, 5 for the second, right? You're increasing your pay by $5, right? You work a job, you get paid $10 per hour. So your pay increases by $10 every hour. See how I'm using the words per, each, every there? Now, with the starting or extra value, this is going to depend on what the actual situation is, right? Let's say you're at a restaurant and you're paying for a certain number of items that you've eaten, and then there's a tip on top of that. That tip could be considered your extra value. Or maybe you get into a taxi cab. Sometimes a taxi is going to charge you a certain amount up front. As soon as you sit in there, it's $5. And then it's an extra 15 cents per mile or whatever the number is. But again, you'd start with $5 just for entering the taxi, and then you pay a rate based on the miles. Get that? So you start somewhere and then you increase or decrease. Or this plus B is like a little extra tacked on, right? Think about maybe a monthly bill. Think about your data plan, right? A lot of people have unlimited data, but not everybody, right? Maybe your cell phone bill is $80 a month starting, right? Starts at $80 a month. And then it goes up for each gigabyte. Maybe it's $10 per extra gigabyte. $10 per, right, each gigabyte. So you really want to start thinking about how the equation can actually have connections to the real world. Because this one equation, y equals mx plus b, we can use this to predict a lot of things in our personal lives. A lot of things have linear relationships. Because a linear relationship or a linear function, right? So this rate of change is constant. If my job, if I get paid $10 per hour, that's what I get paid every hour. $10, right? It's constant. 10 for the first, 10 for the second. You get what I'm saying? Rate of change is constant. I'm going to put that here. That's very important. Constant rate of change. So let's look at a couple examples here. So this equation shows the total cost of a delivery of P pizzas, right? A lot of people are getting delivery now or pickup thanks to all the COVID-19 stuff. Regardless, this equation shows the total cost of buying a certain amount of pizzas. Notice what I said. A delivery of P pizzas. What does that mean? I don't know how many pizzas we bought, right? We bought P pizzas. We didn't buy 6 or 7 or 8. I don't know. This is a delivery of some random number that we call P, right? The variable P. Obviously, the C, you can take a guess what that stands for. The total cost. So look at this little equation here. The total cost equals 9 times the number of pizzas, because that's P, plus 5. What we're going to do is interpret the meaning of the 9 and the 5. Right? What does the 9 and the 5 have a relationship with these pizzas? Right? What is the relationship? What a lot of people want to say, mistakenly, is that there are 9 pizzas, because they see 9P, right? P stands for pizzas, so it must be 9 pizzas. No, not at all. So remember what P is. P is the number of pizzas, right? So this P here is the number of pizzas. We don't know how many pizzas were purchased, but the P represents that. So that means the 9 must represent something else, right? Now I'm going to put C is total cost. Give myself more room here. So, right now, all we know is that this P is the number of pizzas and the C is the total cost. So what could the 9 represent? Well, it's a rate of change, right? Now, when we say rate of change, in this problem, what is it that's changing? I mean, there's technically 2 things, right? You could change how many pizzas you buy, right? You call the store, I could order 12 pizzas, I could order 2 pizzas, I could order 1 pizza. This value can change. And if you change the number of pizzas, won't you change the total cost, right? That makes sense. You order more pizzas, you're going to pay more money. So, this 9 in front of the number of pizzas, well, guess what? This must be the cost of each pizza. So, what this means is that it's $9 per pizza. $9 per pizza. $9 for each pizza. $9 for every pizza. You see how I could just use any one of those words there and make it make sense? So it's $9 for each of these pizzas. Now what could the plus 5 be? Well, we're ordering delivery. You call a place and get something delivered, you have to pay a delivery fee, right? So this 5 would be a delivery fee of $5. That would be the extra value. Or even starting, right? As soon as you know that you're calling for delivery, you're starting off paying $5 because you're getting it delivered. And then you're going to add $9 for each pizza. Or you're paying $9 for each pizza and then tacking on an extra $5 as a delivery fee. So that's the way you want to be interpreting these things, right? The variable will be tied to the rate of change, and this constant term, right, the number without the variable, just represents the extra part or the starting part, right? Let's reverse this. How about we try to make an equation out of a certain situation? So how about we say, let's go, the cost of a phone plan is $80 a month. You must pay an extra $10 for each gigabyte that you go over. I mean, anybody that doesn't have an unlimited plan knows the struggle, right? Going over your data, you go on the internet, right? Because it doesn't shut your internet off. They'll let you keep going over because they want to charge you more money, right? So the cost of your phone plan is $80 a month, and you must pay an extra $10 for each gigabyte that you go over. We're going to write an equation to show the total cost in a month, right? So let's say T equals the total cost for 1 month. It's a really good idea to identify or define your variables whenever you're trying to write an equation. So I'm going to use T to be the total cost for 1 month. And how about I use G to be the number of gigabytes you go over. Right? The extra gigabytes that you use. So let's say total cost, right? So the total cost, okay, rate of change, starting or extra value. What's the rate of change here? Where's that word, per, each, or every? Oh, you mean $10 for each gigabyte that you go over. So wouldn't that mean you're paying $10 for each gigabyte plus your starting value, that $80, right? In a month, you're paying 80 plus 10 for each gigabyte that you go over. Again, that is an increasing relationship. It is possible that they are decreasing relationships as well. Let's just go over one more real quick. Let's show you a decreasing one and how you would represent that and how you would know what's going on. So let's say a plane is at 30,000 feet. So a plane is at 30,000 feet and is descending at a rate, let's say, 500 feet per second. Let's write an equation to represent the current height of the plane based on time. So what I'm going to do is I'm going to let h be the height of the plane, and I'm going to let t be time in seconds. Usually the variables are given to you. That's why I'm kind of just producing them right here. H is going to be the height, t will be the time in seconds. So if you think about it, the plane, right, the current height of the plane. I'm going to write this in two different ways. Let's think about where the plane is right now. 30,000 feet, right? So right now the plane is 30,000 feet in the air. And then it's descending. You would have to know that word means it goes down, but that's what it means. So the plane descends. Oh, look, I used the word rate of 500 feet per second. So you see the word per, but I even use the word rate. It's a rate of change. Now, since it's descending and we're going down, we actually have to minus 500 t. Again, t is the time. You would multiply that by 500 feet every second. 500 the first, 500 the second, 500 the third, 500 the fourth. Now, you might notice this isn't quite in y equals mx plus b form. Obviously, I think I've already shown that it doesn't have to be y and x, right? It could be any letters. H and t, I used other letters before. What did I use before? T and G, right? Yes. If I wanted this to look like my y equals mx plus b, I would just switch these two around. So h would be negative 500t plus 30,000. That's a negative 500, right? So when you move them around, the minus sign in front of the 500 should still be there. So again, negative 500 means you're descending 500 feet per second. The 30,000 feet is the initial value, the starting value. We started 30,000 feet in the air, and we're going down 500 feet per second. That's pretty fast if you didn't take a guess. 30,000 feet's pretty high. This means you would be getting down to the ground very quickly, maybe even crashing. So anyway, that's pretty much everything you're going to need for your assignments for linear functions, and good luck, right? Number of the day for this lesson is 22. Got that? 22. Good old deuce, deuce. See ya.